Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this next lecture in this particular course on analytical, spectral, microscopy applications of inorganic compounds and nanomaterials. In the previous two classes, we have been looking at aspects relevant to that of the thermal methods. Let us continue with it. I have already talked to you on the thermogravimetric analysis, an experiment where you monitor the change in the weight of the or mass of the sample. And we have also looked at another technique or another method which is called thermogravimetric analysis, differential thermal analysis. So, where you look at the temperature difference between the sample and the reference. So, both the sample and reference are heated to the same extent, heated to the same level, but the sample may be more temperature raised or temperature decreased, and that is what you are basically looking at differential thermal analysis. And we looked at quite a few examples. We have looked at how to estimate the compounds present in each of these, even when you have a mixture of compounds using the thermogravimetric analysis, and how the differential thermal analysis will tell you the process, whether it is a endothermic, whether it is a exothermic kind of thing. So, let us today move on to the topic of the differential scanning calorimetry. It is very close to that of what we have seen differential thermal analysis, where you look at the temperature difference between the reference and the sample. Here you will heat both the reference and sample to the same extent with the same profile, the temperature profile, but what you see is either you put the power into the sample or take out the heat energy from the sample. So, that is endothermic or exothermic. So, in terms of instead of temperature raise or temperature decrease, what we look at in differential thermal analysis, here we look at the heat flow difference. Okay, heat is flowing into, that means endothermic, heat is flowing out of this system, which is called exothermic. So, endothermic, exothermic, these processes in terms of the heat delta H. Okay. So, that is the enthalpy differences or heat differences, that is what you are looking at. I hope that basic principle is clear to you. You have a reference, you have a sample, you are heating both of them to the same extent, but reference nothing happens, or with respect to reference there may be some heat taken in to maintain the temperature same, or heat given out of the sample to maintain the temperature same. And that is what the principle basically is. So, that difference in delta H that you are measuring, so that is what you will look at in case of the differential scanning calorimetry. So, which is also popularly known as the DSC technique. Okay. So, you can look at this whatever I mentioned in terms of the words, you can see in terms of the configuration here, and you have a reference, you have a sample, and all of these are put into some kind of a chamber, and where is a heating system as a thermocouple. So, using the thermocouple you can heat both of them, entire system with the same temperature. So, your temperature axis will have only one value. So, that will be keep changing from one to the next to the next. There is no one kind of heating for the reference, one kind of heating for the sample. No, it is the same heating system that goes on into this, and there are many other components are being attached to this. So, the temperature controls, etc., the amplifiers and recording. So, entire thing is connected to the computer to get the data. So, I hope the basic principle of the DSC is very similar to that of the differential thermal analysis, which we saw in the previous class. There it is the temperature raise or temperature decrease, that is delta T you use. Here what you do, you look at is the heat flow in or heat flow out. So, in terms of the delta H. So, you plot here the heat flow or heat capacity, and if it is gone into the system, it is called endothermic. If it has come out of the system, means your sample, then it is called exothermic. Same thing is true in the previous case also. The only difference is here you are measuring the heat, there you measure the temperature. That is all the difference here you have. So, when you look at the corresponding thermogram, differential scanning calorimetric thermogram, if you look at that, you can see not much change. There is a small changes happening, and then you have a big peak, and there is no change or not much change. There is another peak, etc., etc. So, you can see one of them is the glass transition. We have already explained to you earlier in the previous class, going from the solid like to the liquid like kind of a situation, and crystalline or semi crystalline. So, or from one crystalline to the another crystalline. So, these kinds of things, and then melting. Melting is of course the, and then if you go further beyond, you may have some kind of reactions have a degradation happening, any of these. Now, as already you can see from this peak that is shown, the peaks are basically shaded here. So, you have the heat flow, okay. So, in and out. So, in means into endothermic, out means exothermic. So, if it is flowing into, so either way you can draw the reverse also, there is no necessity. So, you have a peak of that kind. So, this peak area you are shading, this area has a lot of importance in terms of quantification. So, any of the peaks that you are getting, okay. So, if this is endothermic, obviously this is exothermic, and this level you can always calculate, and the area can be useful for that. So, endothermic peaks and exothermic peak here, endothermic peak here, degradation. So, if it is amorphous material, there is no change in the crystallinity of that. So, in such a case you do not see any of these except the glass transition, and if you heat to very high temperature, that may break down, or that may get some reaction done, something else can happen, either a reaction or any of these things. Okay. So, just to get a feel what I mentioned here on the board in terms of the area, I have shown another graph over here, which is a DSA thermogram for a small globular protein. So, you can see that of course, x axis is all the time is the temperature, and that is the temperature which you maintained in that whole box that you have seen in the previous slide. This whole box is heated to the same temperature. So, whether it is a reference, whether it is a sample, no change in the heating, but there is a change because something is happening in the sample, therefore, you have a difference in the heat flow either in or out. So, I have stressed that I think several times when I was talking to you about the differential thermal analysis. Now, when I am talking to you about differential scanning calorimetry, the principle is the same. The measurement is the temperature there and the heat here. Okay. So, you can see that heat peak is plotted as a function of heat capacity versus the temperature. You can see the profile of that and this area. So, the excess heat capacity versus temperature curve, that is what is calculated in this particular case. Tm, this value is 350. So, delta H is 100 kilocalories per mole, and delta Cp is 1.5 kilocalories per mole from that particular experiment. These values are not to be taken for every sample, they are not fixed. Okay. So, it is very important, be very cautious about that. So, Cp is the signal that is for the sample and the baseline differences. These are the things, and by the mass, by the heating rate, by the sensitivity. How do you get your sensitivity? Sensitivity is you take for your actual standard, that is sapphire sample, and the baseline difference by the mass or the sapphire, heating rate, theoretical Cp for sapphire, which are known. So, you can get the sensitivity from this, and you can use in this, and you can get your Cp, and that is how it plots basically. So, you feed these values to the program, and the program does. So, we do not really notice what has happened, but that is very dangerous. We should know what all happening on the y axis, what all happening on the x axis, even if machine does all the time for us. Without that, we will not have a feel of the subject at all. Now, you can see that this is for the protein unfolding. You can study by differential scanning calorimetry. You can also study by circular dichroism, which I have not taught to you. Probably I may not be teaching in this particular course at all, which basically measures the optical rotation parameters of a sample at different temperatures. So, the blue curve is coming from the CD circular dichroism, and this one is coming from your differential scanning calorimetry, and you can see the peak point, that is the peak point is the point where some transition is occurring. So, it is going from some kind of a folded mode to a non-folded mode or unfolded mode, the mode where the folding is lost, and that is so you can see the temperature and the extent to which this process consumes energy can be obtained from the area under this peak. So, I hope this is understandable. So, these peaks, the peak position is important, the peak area is also important for all this, and whether the peak is endothermic, whether the peak is exothermic, this is also important. So, all these characterizes, and the x-axis value is also important, temperature, at what temperature is happening, at what temperature glass transition is happening, at what temperature the crystallization, or what temperature the melting, what temperature the decomposition. So, these are characteristics of that material. So, from one material to the other, suppose if the material has an impurity, these temperatures will shift a little bit either to left or to the right. So, these are all possible. So, you have to be this is a useful blessing in disguise. So, we will know if the original value is drifted, that means there is some impurity in present. In fact, you can quantify the impurity also. Is it 1%, is it 2%, is it 5%? In many cases, some of the examples are coming up. So, watch for those examples and make sure that you understood the principle and you are capable of manipulating those things by looking at the examples and be able to calculate those things as well. Let us look at some example to understand the principle that we have studied. We have already looked at the TGA for the same sample, the magnesium sulfate 7H2O. We know that in one step you have a 1 water loss, and you have the step of 5 to 5.8 water loss. There is a small amount of water loss at this. Now, if you look at the differential scanning calorimetric thermogram for that, so you can see for this you get one peak over there, and what is the corresponding scale for here? The scale for this is on the right side, DSC signal, you can see that the negative. So, this is endothermic, and then there is another huge peak which is coming here around 70, 80 plus kind of a temperature, which is corresponding to this particular loss, this loss the water. So, the first one water is giving here endothermic, huge endothermic peak for this one here, and there is another one here, and that is corresponding. So, that becomes the exothermic by the time. So, you have gone to temperatures beyond 200, beyond 250, beyond 275, etc. So, you can see that these three, the two of these are endothermic, one of these is small but exothermic, and that characteristic, that is a characteristic pattern for that particular sample. So, in future when you have a mixture, you can use this signature to identify from the mixture. So, I have already shown you from TGA how you can identify the mixture. So, here from the DSC also you can identify the mixtures. Look at, is it yeah, I was talking to you when you have a mixture. Yes, there is some example given here, but for a different sample. A pure dextran, dextran is a polymer which is a carbohydrate based polymer, which is used quite frequently in a lot of the drug loading and drug delivery applications of that. Okay. So, so pure dextran gives a glass transition somewhere here. So, beyond 220, 230 range. Now, if you have another material PVP, polyvinyl pyrrolidine, and that gives here somewhere around 170. So, is around 230, is around 170. There is a huge gap between them, about 60-70 degree difference is there. Now, if you take a mixture of these two as shown in the B, dextran plus PVP, you can see the dextran. So, depending upon the extent of ratio that you have mixed, so it is not that 1:1 all the time. You can have different ratios, and these peak areas, the peak range will change obviously. So, this from this point to this point is the weight for this, this is for the DSC heat flow. So, that heat delta H value will differ, here the delta H value will differ. So, these are all the things that you can compare, and you can break it, and you can identify the components present in that. So, sometimes it could be a composite which is formed. You are taking A pure, a B pure separately. Now you mix A and B and do some kind of a treatment of that, the blending. So that can form a composite. So in the composite also you can try to find how much of the A, how much of the B, how much of the A is shifted in terms of its delta H and in terms of its position of the x axis, and B how much it is shifted. These are all parameters which you will gauge whether there is a blend is formed, whether there is a composite is formed, whether the composite is not formed. Okay. So all these things will be very greatly helpful. So you should keep looking for even a very minute change in the thing, you should look forward always, and that is what will explain you. So this is for an organic kind of a mixture. You can look at some inorganic example as well. So you can see this is one complex of iridium bonded to acetyl acetone. This is fixed, and this side you have the nitrogen and the iridium carbon bond. So this group you can have just the phenyl group or this kind of a group. It's a big group. So when you have just this one, there is not much change at all in the whole thermo profile, going from somewhere 50 up to about 300, not so changes kind of a thing. That means nothing is happening in that compound. Even if I heat from 50 to 300, nothing is happening. But on the other hand, if I put this moiety in this place, so this moiety in this place, okay, then what is happening? You can find all of them, the glass transition, the crystallization transitions and the melting transition. So the crystallization is, we know that it is a heat is evolved, so it is becomes the exothermic kind of thing, and melting is endothermic kind of thing. So you can see it's written as endothermic arrow down, that means towards up is exothermic. So towards up is exothermic, towards down is endothermic, that is what it is basically. Now you can differentiate these, whether you have a group of this, whether you have a group of this in that complex that you have. It is a single, there is no mixture here. So let us look at some other example. I was talking to you, a lot of application is possible with these polymeric materials which can act as a drug carrier, drug release kind of thing. So what one always looks for in the medical field is, whenever you give a drug to the patient, the entire drug should not be released, should not be put into the flow digestion into the blood flow system. So it should be very slowly, a controlled way it should be released, then it will be of great use. Its therapeutic value will be much greater, and that is what everyone is now looking for. So all the doctors are waiting for scientists to build the molecular systems which can deliver somewhat in a controlled fashion, and which will deliver where you want. These are the two aspects. So targeted delivery as well as the controlled delivery. So these are the things. So in that context, some example how the DSC can help us in that. So this is again dextran, which I mentioned to you in the previous case, and the dextran can form a gel under certain kind of a conditions of that, and in that gel you can put your drug molecule. Here the drug molecule is shown here, it has a certain name, praziquantel, it does not matter. So this is the drug. So we need to find whether the drug is loaded into that, whether the drug is able to be released slowly. So these are the aspects that we need to look at that, and can these be identified by the method of the DSC technique? Yes. So if you take the pure drug, you have a very sharp peak of the DSC here, you can see around 140, and if you look at the dextran, you have in the simple dextran here, dextran which is 70 kilodalton dextran here, and you just take a physical mixture of these two, and then you can see nicely made that. Now you convert this dextran into its gel form, because that is for application that becomes the easier. So in the gel you can see in the D the gel, so you can see very nicely still your drug is there, and this release also has been studied very well, and this whatever the little changes come because of the kind of a the drug release was slow because of the rate at which the swelling takes place during the gel process, and the other studies were already done, that is the swelling rates. So when you look at the swelling rate, versus this the drug release rates, they were comparable. So, it is happening because of the swelling parameters taking place. So, when it swells greater, the drug can come out. When it is the swelling is become compact, then the drug is held up. So, drug stored and drug released, and this kind of a process should happen very slowly, and that is what is called sustained release. So, slow release, sustained release is important, and that is where you are looking for. So, slow release of drug. So, at times people use sustained release. So, that is very important for us, for the medical field, for the benefit of the patient, to have the effect of the drug continuously rather than bursting the whole concentration of the drug at one time, which can cause the side effects much more. So, let us look at a laboratory reaction which is useful in the research purpose, mainly in the solid state chemistry part of it. So, you have a double perovskite, CS2Ag ion Cl6 is the compound, CS2Ag ion Cl6, this is the one. This one is basically contains AgCl6 and InCl6. So, units, these are the units. So, you can see, so there is a silver is surrounded by 6 chloride units, indium is surrounded by 6 chloride units, octahedral unit, another octahedral unit. These are present in the lattice. So, these are octahedra, you call it as. So, if you look at the TGA of this, you can see here there is one weight loss, there is a very small weight loss here, and there is a weight loss of course considerable, about 42.6, quite considerable weight loss. There is another weight loss here which is around 55. So, 55, 43, etc., you can see almost the total thing. So, in the inorganic generally you do not get the weight percentage to 0. Why? Because most often the metal that comes out goes as an oxide or some other kind of a carbide or some other kind of a compound, and that will not further get degraded at the temperature that we are studying. But here you see almost it has come very close to 0 axis. That means the weight is completely lost. That means what does that mean? You have been making some volatile kind of a compounds. So, what are those volatile compounds, etc.? Now, let us look at everything is revealed by this particular thermogram and further assisted by the DSC thermogram. So, the DSC thermogram will tell you whether it is endothermic, exothermic, and your TGA thermogram will tell you basically how much, what extent, what will it fit to. Now, if you look at this, it is a very little tiny, it will not fit to any of these components at all. So, it is a small amount of water which is adsorbed on this particular material solid that you have taken, and that is what is going out. And you can see when you have to move, when you have to throw out the water from the sample, you need to supply the energy. So, that is where you can see is it's an endothermic kind of a process. The next one is the one which is 40-43%, and then this is coming around 539 degrees Celsius, and so this particular peak. So, there is a 43% of weight loss is there, and if you look at that, is 43% weight loss. So, this one cesium silver chloride. So, this is the compound and this is volatile at that temperature, it will go out. So, this is can be evaporated as CsAgCl2. So, this comes around 44% of weight loss. So, if you calculate exactly that, it comes to 44.5. So, you can see close by, because you have something last here also. So, you can add that, it will be making all that. So, it's so that is what is one other thing. The next one happens starting from 600 up to about 850 or 900 this weight loss. And if you look at the DSC, you have one peak over there, another peak over here, and small peaks are there. So, they are between 750 to 800 in that kind of a range. So, what is happening in that particular range? So, you have your disintegration of the original compound, which is CS2Ag ion Cl6 going to CsAgCl2 plus CS ion Cl4, and of which this is the one which already sublimes, which already evaporates basically. So, this is gone, and what is there? CS ion Cl4. So, this CS ion Cl4 further decomposes here. Okay. So, that gives you CsCl and ion Cl3. Okay. So, in the process you also have the AgCl part. So, these things get evaporated here at these temperatures 750, 800. So, therefore, this further breaks down to this, and this is also volatile. So, you have hardly any mass left in this. So, all these processes basically require energy, therefore, they are all endothermic. So, you can see an endothermic peak, a huge endothermic peak, another endothermic, another. So, you can, if you take the area of each of these, you can also quantify the extent of how much happening, and from that also you can recalculate and fix. This is corresponding to this moiety, and this is corresponding to this moiety, and the other one is corresponding to the other moiety. All these things can be very well. So, that means even in research you can follow up by using a combination of TGA and DSC that we have looked at here. So, I hope you got that point in this. So, let us look at some thermal analysis. I am using the term thermal analysis as a common. So, there could be a TGA, there could be a DTA, there could be a DSA, all these kinds of things, combination of these techniques that we will be using. So, that is why I use the word. In fact, in the literature people use the same. Some organic. So, organic but application oriented. So, not that organic molecules or something. So, the polymers have got a lot of application orientation. So, therefore, we are looking at such kind of materials. So, in fact, they use this kind of a technique. Okay. So, here we have, let us look at first on the right side of the panel. These are thermograms. So, that means you have a weight and going down. So, they have taken the 10 milligrams of the mass going down to the 0. Some of them may not go down as they stopped, etc. So, this one and this one. So, what are these labels? PI, PTFE, LDPE, PVC, etc. You see the figure caption, you will find the PVC is polyvinyl chloride, PMMA is polymethyl methacrylate, PDFE is low density polyethylene, and PTFE is polytetrafluoroethylene, aromatic polypyromelitidine. In case if you have missed any of these, you can Google and get it. So, do not be so much scared of that. So, these are all polymers which are used for variety of applications. Why we are doing? Because they are used for variety of applications. So, you see the weight loss happening. You can see how much weight loss percentage you can find, and temperature at which. How will you get? You just make the dW by dt or dm by dt, which is called differential thermogram. From that you can get exactly the temperature at which is happening. So, this dW by dt value for this, dW by dt value for this, for this, for this, for this, here there are two processes, one is here, other is here. Okay. So, you can get two. So, all of these are very different. So, that dW by dt values differ for each of these. So, dm by dt or dW by dt value, these differ. So, using that comparison you can tell what is this polymer, whether this polymer is pure or not pure. If there are any impurities, you can find out that as well. To what extent, what percentage. In most of the applications people look at the polymer, how much impurity. Okay. They may not be so much bothered about what kind of impurity. They are bothered not at that stage when some other unwanted property comes into picture, or your main property got stuck or got diminished. In that case people look for what are those. So, these are all done at 5 degrees Celsius per minute in nitrogen atmosphere. Look on this side, another example which is shown for the PVC, which is this one. This is with a chloro bond, and the PE, all 4 bonds are hydrogen. This is a N, means repetitive. So, monomer structure is shown here, and that is N number of times, and PTFE. So, you have fluorine, 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 fluorine. So, all the hydrogens are replaced by this. So, would you expect for each of these polymer to have the same weight loss, same temperature at which the weight loss takes place? So, for PVC you have one here, you have one more here, as you have already seen on the right panel, and the PE has got here. So, if this one is below 300, this one is around 400, and this one is a little bit above 400, and this is above 500. So, each of this, now this one here, and this has a CCl bond, and this is coming at the lower temperature, means lower energy, Kt is energy correspond to that, Ch is a higher and Cf is much higher. So, we know very well the CF bond requires a greater energy to break as compared to CH bond as compared to the CCl bond. So, therefore, the CF bond energy requires greater than the CH bond energy, which is greater than the CCl bond energy. It follows that. So, this polymer is the PVC polymer, and this polymer is the PE polymer, and this is the PTFE polymer. So, you can see that the polymers can be. So, you can also identify the amount of each of these. If you take a mixture of these polymers and make another polymer composite, then you can also find out these, because the temperature differences are quite much. So, therefore, temperature at which they break down, that is the dm by dt, are different. So, therefore, you can easily make out. I have a lot more examples, and I will continue those things in the coming up class. So, some more examples of the organic type, then we will also see other general applications, where in kind of a food analysis, in clay, in kind of many medical, many kind of things. And then probably I can ask you to take up some of the examples and work on your own to explain these ones. Thank you very much.